We study ferrous metals and their alloys. Now for that we have considered that what are ferrous metals. Now what are the ferrous metals? The main constituents are iron, and after that we have to add an alloying element so that the property can be increased. Now what is iron? Iron has a very uh, essential property that it is a ductile metal, can be converted into either sheets or either it can be elongated to the wires. Again, it has a good conductivities. So these are all the important features, that's why the ions are used. Now again, one more property that iron has, that it has various allotropes. And what is allotrope? Various crystal structure at various temperatures. So from the diagram we can see here, at 1500 degrees Celsius above, that is 1539 is the boiling point of the iron, and above that it is in the liquid form. Then below that it is called as a delta ion, where the crystal structures are BCC. Again, below that temperature it is converting to the gamma ion, where the crystal structure is FCC. Again, further cooling, it is converted to alpha ion, that is the crystal structure here is the again BCC. Again, during the cooling time, the magnetic properties of the metal can be changed. So that is a basic property of the iron. Then we can see the various crystal structure. It is a BCC structure and it is a phase structure. So it is a BCC means the body centered cubic structure, where all the atoms are at the 8 corners of the cube and one of the atom is at the center. It is called as a BCC structure or a body centered cubic structure. Then FCC is nothing but all the atoms are at 8 corners and each atoms are at all the 4 faces of the cube. It is called as a phase centered cubic structure. So due to the difference in temperature, the structure of that crystal structure of the iron changes. It is called as allotropy. Now why we are studying this? Because what we have to do, we have to add the alloying element, that is carbon, into the iron. So what are the use of for that allotropes? Now in that, iron is heated up to the melting point, and after that only we can add a carbon into that. Now due to that, what are the different phases we occur when we heat that iron up to the melting point and we are adding a percentage of carbon into that. So different phases will occur. That's why we are studying the allotropy of iron first. Now we see what is the iron carbide phase diagram. Now it is nothing but when the ions are heated up to the melting point and a small quantity of carbon is added. When we cool down it, we get a various phases in that, and they all each phases have a different properties and the different allotropes. Now we can see that iron carbon diagram phase diagram describe the iron carbon system of alloys containing up to 6.67% of carbon. That means solubility of carbon in the iron is up to only 6.67%. Then it discloses the various phases, compositions and the transformation occurring with the alloy during the cooling or heating. The content correspond to the fixed composition. That means at 6.67 percent of carbon, the alloy is called as the, that is iron carbide, and the chemical formula for that is the Fe3C. So we can see, now we can go for the actual iron carbide diagram, where on x-axis there is a composition, that is the percentage of carbon, and y-axis is the temperature. Now from that allotropy we can see above liquid it is above 1539 degrees Celsius, it is called, it is in the liquid form. Again on further cooling, it converted into different allotropes, that is it will convert to delta ion, then it will convert to, after that delta ion it will convert to gamma ion, and again it will convert to alpha ion up to the room temperature, and each phase have a different crystal structure. When we add the carbon into that ion, again we get a various compositions. Now from that we can see on y-axis is the temperature, x-axis is the percentage of carbon. Now from that we can see here various phases. Here it is called as the austenite phase, here it is called as the ferrite phase, then there is a pearlite, then there is cementite, then there is a cemented at 100% at a 6.67% of carbon. Now various phases can be seen here. Further cooling, two things are changing here. First is the crystal structure, then the phase, then the magnetic properties are changing here. So we can study that. Now from the diagram we can see here up to 2% it is called as a steels. Then above, on further addition of the carbon, the steels are converted into cast iron. So up to 2% it is steels, and further adding of the iron carbon into the iron, it will convert into cast iron. Again, both the phases, both the uh, metals will have different property according to the percentage of carbon in that. Now further we can see that here it is a delta iron. Again, now from the diagram we can see here it is called as alpha delta ferrite, where the iron is in the delta form and the crystal structure is BCC, and again the carbon percentages are minimum here. So it is called as a delta iron, delta ferrite region, where ferrite indicates that the carbon percentages are very less. Now further cooling, it will convert into austenite phase, that is a gamma iron, where the crystal structure is FCC. Then again it will convert into, if you cool down, again it will convert into alpha iron, where again the crystal structure is BCC and the carbon percentages are less. So for from delta iron to austenite, then austenite to alpha, these are the transformations are taking place. Again the different another types of diagram we can see here, that is the same as that of previous one, but only the difference is that here it is in the temperatures are in Fahrenheit, and same thing. Now you see the different phases. The phases are, first from the diagram we can see that above that 1539 degrees Celsius the iron is in the liquid form. Again the ferrite. Now ferrite says that the carbon percentages are very less. Okay. Now in that delta region, the alloy is called as a delta ferrite, where the carbon percentage are very small in quantity. Now further cooling, it will give to the austenite phase. Again we can see maximum concentration of carbon in delta ferrite is 0.09 at 151439 degrees Celsius. So same thing, where the carbon percentages are very less. Again the crystal structure is BCC. Then next, after the further cooling, it will convert it into austenite. It is nothing but the interstitial solid solution of carbon in a gamma iron. Then austenite has FCC structure, permitting high solubility of carbon up to 2%, and the temperatures are given. So this is the phase. So first phase is ferrite, second phase is austenite. Now austenite does not exist below 723 degrees Celsius and maximum carbon percent up to. So above this ranges, it is not called as austenite phase. Now you see next phase is called as alpha ferrite. Now from the name itself we can see that in the by going through the allotropy of iron, alpha iron is having a BC structure, and here ferrite is also considered, where the carbon percentage is 0.025 at 723 degrees Celsius. This phase is called as alpha ferrite. Again the next ferrite is called as a cementite. Now in this cementite, iron carbide intermetallic compound having a fixed composition of Fe3C. Cementite is a hard brittle substance. That means the compositions are very high in this phase of carbon. Now we can see here up to 2% of carbon, it is called as a steels. Alloys containing to 6.67 carbon experience a eutectic transformation, that is at 100 and that is 1147 degrees Celsius. The carbon percentage is 4.3. It is called as a laterite phase. Then next point is the in practice hypoeutated or eutectic alloys are used. These alloys are called as a cast iron. That means the properties are changing here. The malleability or we can say ductilities are changing here. It is become more brittle when we add a carbon percentage above 2.2% of carbon. That is the cast iron phase. Now we can see when the temperature of alloy from range reaches to, it contains primary austenite crystals and some amount of liquid phase. The latter decomposes into fine mixture of austenite and cementite. It is called as a ladybite. Now if we go to this diagram, now from here we can see 4.3%, it is a combination of austenite and cementite, and it is called as a ladybite phase. Now all iron carbon alloys experience eutectic transformation at 723 degrees Celsius. The eutectic concentration is 0.83. when the when the temperature alloy reaches, now from here what we can see that at 0.83 it is called as a pearlite phase. Here 100% of pearlite phase is possible. Again, one more thing is important in the iron carbide diagram is the critical temperatures, where that at that temperature the various transformations are taking place. Now one, that is the upper critical temperature, that is A3 is the temperature below which the ferrite starts to form as the result of ejection from austenite in the hypoeutectoid alloys. Now from the diagram we can see A3 is here where the austenite is converting into ferrite. So that is the A3 upper critical temperature. Then second critical temperature is called as critical temperature at, that is ACM, is the temperature below which cementite starts to form austenite as a result of ejection from austenite in the hypereutectide alloys. Then the fourth type of temperature is that is A1 is the temperature of the austenite to pearlite eutectide transformation. Then below this temperature austenite does not exist. Again magnetic transformation of temperature A2 is the temperature below which if alpha ferrite is ferromagnetic. Now from that here we can see ACM is this line where austenite is converting into, this phrase is called as a ACM, that is the upper critical temperature, where austenite phase is converting into either into cementite, pearlite or ferrite. Here it is called as a A3 temperature, upper critical temperature. Here it is called as a A3 temperature where austenite is further converting into the ferrite region. Again A1 is there where austenite is converting into pearlite region and there is no further austenite phases in exist. Then A2 compared here, it is a A2 temperature where all the phases are converting into cementite. So these are the various transformations are taking place when the alloys are there. Now we can see the phase composition of iron carbon alloys at room temperature. Now hypoeutectoid steel, that is from 0 to 0.83 percent of carbon, consists of primary ferrite and pearlite. Again eutectoid steel entirely consists of pearlite, that is 0.83 100% pearlite region phase can be seen. Again hypereutectoid steels carbon content from 0.83 to 2% consists of primary cementite and it is called as a pearlite. Then cast iron is from to 4.3 consist of cementite ejected from austenite according to curve ACM. So these are all the phases that are can be seen in the iron-iron carbide diagram. So that is all about the iron-iron carbide diagram. First we can see the allotropy of iron. Again, various allotropy is nothing but the various crystal structure of an metal at different temperatures. Again, in that we have seen the delta ion, gamma ion and the alpha ion. So when the temperature is decreasing, the ion is changing into different crystal structure and it is called as allotropy of ion. Again, for adding, for the making a alloy of iron, we have to add carbon into that, and after adding the carbon into the iron, we get a different phases. So that is, the phases are ferrite, austenite, then cementite, pearlite, ladurites. All these things are we are getting when we add iron into the carbon into the iron. Then again, up to 2% of carbon, the steel is called the metal is alloy is called as a steel. Again, it has a different properties. Again, further adding to carbon above 2% up to 6.67%, it is called as a cast iron. Again, the properties are physical property, mechanical properties are changing here. So that is all about the iron and carbide diagram. Thank you friends for your attention.